Alright, silly people, here's the situation. This time we have a 1 kilogram point mass that is hovering above a sheet of metal of uniform mass density. Um, and we are going to be calculate the gravitational force in the z direction, so I guess this way, um, on the point mass due to the sheet, right? And the first part of the problem is actually an analytic proof. We have to get to this equation for the uh, z component of the gravitational force. And so I just typed that up in LaTeX. Of course, the equation to calculate force, you have to start with the differential of force, which is, Newton's gravitational constant times your mass times your differential of mass, divided by r cubed times the vector r, where r is like the total distance between um, the center of the mass of the sheet of metal and where the point mass is, and the vector r is like that distance is a vector, right? Um, so if you want the z component of that, though, you just replace the vector r with just z, and then down there I explicitly wrote out what r cubed was, which is the square root of x squared plus y squared plus z squared under a square root and then cubed for r cubed. To get it in the form where it's a dx dy, you use the fact that the mass times the mass differential in this situation is actually just the surface mass density times the dx dy to get that sort of area mass. And so now you have this dfz with all these things that you wrote down, and then you just take the integral of that with respect to x and y, which the bounds for that are both minus L over 2 to L over 2, right? Then the next part of this is, do the code that does this. So I think I want to do it inside out. We're going to do both of these integrals, and we're going to do both of them via Gaussian quadrature, right? And I want numpy, and I want matplotlib.pyplot as plt. And so we're going to have a function which represents the integrand itself. I'm going to call that lowercase f of x, y, z, but not to get too much into that now. We're also going to have it's going to be a function which represents the first integral of the integrand with respect to x. So that I'm just going to call capital F, and it is going to be dependent on x and z, I think. Or no, it's going to be dependent on y and z because it's running over all the values of x, right? But then outside of that, there's going to be another function which is actually going to calculate the z component of the gravitational force, which is going to be f sub z, which should just be a function of z. And this is the one where I'll do this first. So it's Gaussian quadrature. We have to set up n equals 100 sample points. We need the bounds, which is a equals minus L over 2, b equals L over 2, and then x comma w equals Gauss xw of n, right? This is just more of the Gaussian quadrature shell of code that was done in the textbook. Should define what L is. For this guy, it's 10 meters on either side, so I'm just going to do L equals 10 up top. And even I want to give these some subscripts so that we don't get them confused with the actual x and the actual y, and then the other Gaussian quadrature that we have to do. So I'm going to give this one, since it's an integral over I, or over y, it's going to be x sub y, w sub y, right? And then you do your xp line, where I'm going to subscript it y, which again, I'm just going to kind of steal this from the Gaussian quadrature code that we've been using for everything. Well, it feels like the last 5 problems or so. This guy here, where again I'm going to put subscripts in places. So this is going to be xp sub y, wp sub y, and this is going to be sub y on this x, and this is going to be sub y on this w, and should be good there. And I'm even going to do a sub y on this s here, right? This should be subbed y, this should be sub y. This is going to be sub y as well. So I want the k's also subscripted to keep everything separate and clean, even though it's kind of gross looking. So once that integral is done, it's the integral over y. So actually the first argument of the function, which you're going to call, is going to be capital F. The first argument is xp sub y index k sub y. The second argument is actually z, which we're going to plug into this function, and we're going to return s sub y times physical constants. So g was 6.674 times 10 to the minus 11. And then, what else did we need? Sigma, which it's the surface mass density, so it's, 10 metric tons divided by 100 square meters. So 10,000 divided by 100. I'm just going to write that, 10,000 divided by 100. And so, yeah, you return return the result of the integral times g times sigma, and also times z, according to just that line there. Cool. Now we can write out what this function is. Again, it's going to be the Gaussian quadrature code again, where n still equals 100, a is still minus L over 2, b is still L over 2. That hasn't changed yet. This Gaussian quadrature is going to be subscripted x everywhere instead of y. xw, n, and then, yeah, it's pretty much the same sort of lines here. You can probably do this in a way where you create like this, you use the same like lists to do both of the Gaussian quadrature integrals. But I wanted to do it this way. I think it's more readable. If I do it like this, especially since we're going to be doing like, it's like doing 100 integrals for every one integral step that's in this. So every step of 100 in here ends up being 100 steps here. So integrals on integrals. And then you do your s sub x equals 0, and you run over your 4k sub x in range n. Did not mean to run the code yet. And then in that loop, you sum up s sub x, give it wp sub x index k sub x. Realize I'm fat fingering quite terribly. And then little f, this is an integral over x, so we're going to have the first argument be the xp sub x index k sub x. Then the second argument can be just y, and the third argument can be just z. and then we return s sub x for that. Finally, the first function that all of this is based on is just the integrand itself, which is just that fraction. So I'm going to do x squared plus y squared plus z squared raised to the 3/2. I'm mixing Python with LaTeX now, and it's even minus 3/2. Just looking at that integrand. So with all of that, I should be able to create an input list, which is just going to be ZLS, which is going to be a NumPy linspace. It wants us to create a plot from z equals 0 to z equals 10 with 100 sample points along each axis. That means 100 sample points for the Gaussian quadrature. I assume we can use 1,000 points whenever we actually do the input list and run an array through the functions. And then we can, this integration method should be array safe. So I'm just going to go straight into the plot line where we plot ZLS versus f sub z of ZLS. And you get something like that. So it smoothly decreases in gravitational force the further you move away, which makes sense, and it's like an inverse squared law, so that's all sensible. The weird thing is that it sharply decreases to 0 whenever you get so close that you're touching it, which is a weird thing to think about physically, and it's probably not commensurate with physical theory. And I mean, Newman suggests that there's a way to fix this. I think that the really only way to fix it is to increase the lower bound of your input list. So if I increase this to 0.1, it still has that little bit of a tail, but if I increase it to 0.15, that's a little bit more sensible looking. We can just ignore the weird behavior close to 0, as physicists do. All right.